Okay, so guess what? We're going to learn how to take the derivative today of a natural log, of an exponential function, of a log function, all of these. Okay, so this is all on your formula sheet. Okay? All on your formula sheet. Okay, so the derivative of a natural log of x is equal to 1 over x. It's the graph 1 over x. Okay, so what if it was something in, like it's not just an x, it was maybe a 3x or a 5x. 1 over u times the derivative of the inside, du dx. Very good. It's been proven. If we want to use limits, we can. Oh, so if this is derivative of this guy is 1 over x, then this is 1 over u times du dx. So the only difference here is there's something on the inside of our natural log, like 3x plus 5. So we always have to multiply by the derivative of the inside if it's not just an x. Okay? So if our inside of our natural log is not just x, it's something in terms of x, so 4x plus 5, right? Then we multiply by the derivative of the inside. Okay, derivative of natural log of an absolute value of x is still 1 over x. We're going to prove that today. And so the same is true over here. 1 over u times du dx. The derivative, so if we're dealing with a base other than e, right, because we practiced deriving e, if it's other than e, the derivative is, again, just like e, it's equal to b to the x times, though, the natural log of our base. So that's the derivative for exponential function. And so what would this guy become? It's b to the u. B to the u times, we still need natural log of our base, and then times the derivative of our inside, or exponent in this case. Okay, and the derivative of a log function is 1 over x natural log b. Yep. So a difference would be, for example, if I derived, an x would just literally be natural log of x. Find the derivative of natural log, which is 1 over x. One with a u would look like find the derivative of natural log of x squared. Okay, so that would become 1 over x squared, because 1 over our inside, times the derivative of the inside, 2x. This guy? Okay, so an example like that would be, say, 2 to the power of x. So if I derive 2 to the power of x, that would be 2 to the power of x times the natural log of 2. Okay, if we had u, we had a function maybe 2 to the power of x plus 1. No, let's make it interesting. Sorry. Let's do 5x plus 1. Okay, so this is when our derivative is not just a variable x. It's more than that. And so the derivative of this guy, using our formula here, so would still be 2 to the power of 5x plus 1 times the natural log of my base, which is 2, and times the derivative of our exponent, because that's our u. And so what's the derivative of the exponent in this case? 5. So times 5. So really you're going to have to rely in the beginning on your formulas here. It's on your formula sheet, these formulas.
Wait, so this entire box?
Entire box on your formula sheet. I believe it's all in terms of u, though. If you want to grab them, I gave out the yellow formula sheets yesterday. It's all in terms of u, which, I mean, yeah. Then it's just, yeah, exactly. Yeah. Okay, so this would be 1 over u, natural log of b, times du dx. So times by the derivative of the inside there. Man, it really is no fun skipping trig. Okay, let's differentiate this. So what would be the derivative of this guy? Yeah, and the reason I wanted to show you the little proof here. Okay, let's rearrange this function. I'm going to show you proof by implicit differentiation. So I want to prove to you that the derivative of this function is going to be 1 over u. That's my goal. I want to prove that to you. So I'm going to write this in exponential functions. What's the base here for dealing with a natural log? So e to the power of y equals u. So I'm going to derive this. Okay, the derivative of u would be du dx. Can we make this an x instead? Make it a little bit less confusing. There we go. Because we want to derive it in terms of x. U is just usually something in terms of x. Usually something in terms of x. You could use u as your variable if you want, but it's something in terms of x. So 3x plus 5 could be a u when it's just not something other than just x. Okay? Where u is a function of x. Okay, so I'm going to derive this because we know how to derive this guy. So I'm going to derive this guy. What's the derivative of e to the y? E to the y times the derivative of the exponent. What's the derivative of the exponent? Y prime equals derivative of x is just equals to 1. Okay, so we just derived this. So we found the derivative of this guy. So getting y prime by itself, it's equal to 1 over e to the y. And what is e to the y equal to? E to the y was equal to x. And so that's the proof, that the derivative of natural log of x is 1 over x. Okay, that's just the proof. Yeah.
So why isn't e to the y prime
Okay, next guy, let's try this guy. So derivative of a natural log would be what? 1 over our inside times the derivative of the inside, which is 8. So it just becomes just 1 over x. The 8's cancel out. Cool.
Does this like always happen?
No. 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 I like if it was a square. Okay, that was, which one? I skipped number 1 and 4. Number 5, how would we start to derive this, Greg?
You would well, since it's like a u, right?
Mm-hmm.
You would
Start where?
You would go 1 over.
Not yet. Okay, so we're work from the outside in, right? So what changed? So we're first start with 4. Thank you. Great. All to the power of 3 times the derivative of the inside. I'm going to use brackets here. Derivative of 3x squared. 6x, derivative of natural log of x. So plus 1 over x. Okay, so, or how else could you write that? X to the negative 1. So if we wanted to simplify this further, I would factor out x to the negative 1. Okay, so this guy is 6x plus x to the negative 1. Why? Because if I had to find my zeros, I would want to figure out, right, if I wanted to find y prime, when y prime 0, we need to have this in factored form. So factoring out x to the negative 1. Okay, what is that going to leave inside my brackets? 6 what? X squared plus 1. That looks way better now. Right? Now I could actually determine, well, in this case it's a plus 1. But if we wanted to, we could determine what would make this a 0. Yeah. Because it's a rational expression. So rational expressions, we always have to add them together. So another method you could have used is get a common denominator. So multiply this guy by x, gives you x squared over x. Then you can bring them together because it's a rational expression. And then we just pulled out this 1 over x. Yeah? It would be an asymptote. Oh, no, sorry. Our function, whenever we have a natural log, what's it would be asymptote. Why would it be an asymptote? What's the domain? What's the domain of a natural log of x? Has to be greater than what? 0. Has to be greater than 0. You can't take the natural log of 0. So here we know this function, x is greater than 0. Right? Okay, let's go to this guy. He's beautiful. Okay, this is super ugly. Yeah. No. My recommendation for you, if you something this ugly, is let's use our log laws to expand it first. So yuck. That's disgusting. Okay. Fine. I don't know. Okay. No. Okay, so we're going to make it prettier. We're going to make this a lot prettier. So what would it become if I wanted to expand this first? Y equals, not y prime, y equals. Natural log of x minus natural log of x squared plus 1 to the power of a half. We can still make this even nicer if you wanted to. Bring the 1/2 in front. Now, is it as ugly? No. It's not as ugly. Okay, let's derive this now, because it's not so bad. Derivative of natural log of x is 1 over x. Okay, minus, we have a half times this derivative. It's our constant, so you can just leave the constant in front. Derivative of natural log of x squared plus 1 becomes what? Okay, 1 over our inside times the derivative of the inside. X squared becomes 2x. Okay, so we can simplify this a little bit. How can I simplify? The 2 and the 1/2 here. Yeah. So y prime is equal to 1 over x minus x over x squared plus 1. That's not so bad. Or we can get a common denominator, right? If I was actually looking for zeros, I'd have to continue this by making a common denominator, right? We know how to do that? Okay, let's go on then. No? Too fast? We're good. Go back. Okay. where is it increasing? Where is it decreasing? Where is there a max? Is there a min? So if we just sketch it. Just standard log graph looks like that. Right? Remember this? Usually the x-intercept's at 1. And it goes straight down, sorry, like this. So because it's the inverse of an exponential graph. The exponential graph looks like this, right? Okay, I want to show you something. So at x is greater than 0, we're going to break this when x is greater than 0 and when x is less than 0 because it's an absolute value. If it's positive, then what is absolute value of x equal to? Just x. Good. And so we could derive, so if at x is greater than 0, the derivative of natural log of absolute value of x, as long as x is greater than 0, is equal to just 1 over x, because this is natural log of x. Sorry. I know. I'll make it another color.
Make it a full L.
How's that?
Oh, that's good. A little time wasting.
Okay. A little time wasting. So when x is greater than 0 or less than 0, then what is absolute value of x equal to? Negative x. Okay. So that means that we're going to deal with y equals the natural log of negative x. What's the derivative of the natural log of negative x? So first we do 1 over the inside times the derivative of the inside. What's the derivative of the inside? Negative 1. So what does it actually end up equaling? 1 over x. So it doesn't matter if it's greater than 0 or less than 0. Because we had to multiply by the derivative of our inside, we can say that no matter what x is, the derivative of the absolute value of natural log of x is 1 over x. Yeah? This one is, this one, sheesh. Sorry. Thank you. Okay, I want you to try 8. Give 8 a shot. Guys, give a try on number 8. Why doesn't the absolute value matter in this function? Yes. It has to be positive anyways. Can you take the natural log of a negative? No. So it has to be greater than 0. So this function is actually equal to the natural log of 3x squared minus 5. And that's why their derivatives are also the same. Because with this function, you can't take the natural log of a negative. So there are no negative values of x. Well, actually, there could be because it's squared in this case. Yeah. But this inside has to be greater than 0. And sorry, guys. This is getting in the way. I know, hey? If you have like a tablet, you could technically. Okay, so derivative of this guy, you should have had 1 over the inside times the derivative of the inside, which is actually 6x. So it's really actually that simple.
Oh no, I got it right.
I don't know if I want to do this one. Okay. No. That's for exponential. There's a vertical asymptote, though. Yeah? Yeah, it's gone. Yeah. Okay, this is a proof. We're going to skip. Or do you want to go through the proof? Okay. Let's try this guy. So we're using this on the other page. It said the derivative of b to the power of u was equal to what? B to the u times natural log of u times, sorry. Natural log of our base times the derivative of our exponent. Okay, so let's derive this guy. Here's my base. So the derivative of 8 to the power of x to the power of 4. So what stays the same? The b to the u's, right? So it's our original function, 8 to the power of x to the power of 4, times the natural log of our base. What's our base? 8 times the derivative of our exponent, 4x cubed. Done. Okay, this is another proof. Move on. Okay. Unless you want to prove it, you just have to change the exponential and then derive it from there. Implicitly. That's how you prove it. Okay, so the last guy. What's the derivative of a log function? What's the derivative of a log function equal to? Look it up on your 1 over. So I'm going to keep this in terms of u. So u natural log of your base times du dx. Okay? Where is this? Right there. Okay. Okay, so this guy, if we derive him, y prime equals. So it's going to become 1 over u times the natural log of our base. What's my u value? What's my u value? It's the inside, right? All of this is your u. So 7x squared plus 4 times, so that has to be in brackets, natural log of my base. What's my base? 3 times the derivative of the inside, which we actually could just throw on the numerator. What's the derivative of our u? 14x. I'm just going to throw it up top. I just, instead of, oops. Okay, so, sorry. So I had 1 here, right? Okay, and so times the derivative of my inside was 14x. So I just put it on the numerator. That's all. Okay. So your homework is practicing this. Do you have it on your list? Yes, you have it there, right? Yeah. Pardon me? This formula for the derivative of a log. It's on your formula sheet. Okay, so we're looking at our formula sheet to derive these things. Okay? That's it for today's lesson. It's short and sweet. We have lots of time to practice homework and get our homework done. Yeah? Yeah? If you get it done, you can leave. Today's assignment.
Do we have a test back before you get to sign our homework?
Oh.
Let's do our test back.
No, it's not ready.
You can send them back.
Yeah, you don't mind? Okay, close up your stuff for a sec. Okay. Where's Miles today, hey? Is he in rugby? Oh, you're right there. Oh, there. I'm like, there you are. Okay. Speaking of miles, miles faster. Trina. Oh, wait. Weird order. There you are, Trina. Yep. Vincent. Ron Paul. No, it's actually Cam. Wiley. Secret. 1, 2. Landon Van Berkel. Muse. Graham. Greg V. Vandervinny. Kate.
And then you did just as good the one time.
Kate. Tyler. Van. Vicky. Bennett.
No, that is such a dumb.
Landon. Landon Tice. Jamie Prince. Shannon Vogue. Hey, there's a bunch of you who have to get assignments back into me. If you don't want to rework it, you know who you are, just give me how it is and I'm going to record that mark. Let's argue in a second. Jonas? You're good at this game?
Well, I was just walking over.
Mel. Greg H. Just hold on for a sec, just a sec. Greg H. and Adrian. Oh wait, and Ben. Okay, take a look. When you're done looking through it with a fine-tooth comb, you are welcome to ask how to do things if you're lost. Throw them on the desk upside down when you're done.
I tried to do that, but my pen wouldn't let me, and I couldn't change it because it's off. So I tried to correct it.
Didn't look like you tried to correct it.
I would argue,
The right
if you look
0.5
at this
there.
really closely, there's
No,
a little white hole.
No, sorry.
A white hole.
Nice try.
But how is that not a local max?
Endpoints cannot be local max or mins.
When did we talk about that?
Jim Ashton taught you that. Jim Ashton. Mr. Ashton did. He taught you local max and mins in the derivatives. Was it derivatives? Yeah, the derivatives you did. Okay, so endpoints cannot be locals because a local has to have two sides to it. So you can see the increase, decrease, or decrease, increase. Right here. No. They can be absolutes. Yeah.
I got number 9 right.
This is a problem. When you put in 3 things, the computer says, sorry, you got it wrong. So how, like, I'll think about it. I'll think about it. When you're done, leave it here so I can take a look. But
So, you know, I have a question about the reason I didn't include this as a CP is because I never changed
but it's still critical value. So it does affect where, if you're doing, it does change where it's concave up, concave down. So yes, it doesn't change sign, but you have to show at -1, it doesn't exist.
Okay, that's what okay.
Yeah, so you still have to put on your number line. It can make a big difference, especially in a function that's maybe like this and then this.
Okay.
Okay?
If you don't think that's an open circle, you don't have eyes.